Thank you very much, and also thank you very much the organizers for this very nice conference, and also for giving me the opportunity to give a talk in this very nice conference. As you can see, I tried to put it a little bit in the topic of quantum harmonic analysis from the title, okay? And you can also see that this talk is based on a collaboration with me and Bauer and Robert, that is here today. There he is, yes, that's true. So that's it, okay? And the plan of my talk is the following. So we are going to discuss pseudo-differential operators, Orlicz spaces, and also Orlicz Schatten classes, etc. And we will put this in the context of quantum harmonic analysis, okay? Actually, about the quantum harmonic analysis, I would say that when I was a PhD student, I started very much in the style that several of you are working with, that you are working with, let's say, something like a convolutions, etc., with operators, etc. But in the end, I came to the dark side. So I started to continue and just looking at them and purely on the symbol side of the Weil quantization. And for me, actually, a lot of the arguments became much more clear somehow. But I would also say that if you, for example, would like to continue in the way that's in the preceding talk in a more geometric direction, I think that you should not do like that, okay, what I did. So this is purely on when you have an analysis on RD or something like that, and you're working with the usual phase space. So the talk is based on the following papers, actually. So we have just recently get this on the archive, so it is not submitted anywhere. But of course, you can see that in the LP situation, I have myself an old paper from 2002. In that time, I didn't know anything about Werner and his contribution, and it turned out actually that some of the Young type results that I presented in that talk, in this paper, they existed already in the Werner's paper from 1984. I can also say a little bit that the first time I came here to Vienna and met Hans here for the first time, and also Charlie Gröchenig, as well as Elena Cordero, I spoke about these Young type results. Oh, okay, and here you can see those guys that I have collaborated with in this paper. So that's it, okay. So the basic definition, so you have seen a lot of things already, but we can actually put the pseudo-differential calculus slightly more general. It was a little bit mentioned by Robert before, okay. So instead of having the Weil quantization or Nirenberg quantization, you can, for any matrix A here, you can define your pseudo-differential operator in this way, okay? And it turns out that a lot of analysis work in this setting. But if you try to make it a little bit more general, then I think that you will get a little bit more, then it becomes a little bit more cumbersome with the formula, etc. But at this level, you can usually work, okay? And in the case that you take A equal to 1/2 times the identity, you get the Weil quantization. And if A is equal to 0, you get the normal or Nirenberg representation. Okay? That's it. And here is the classical definition. One way to define the Schatten classes, if you want to, we can also start on P, go from 0 to infinity. So this is you have a Schatten P class. T is a linear operator from L2 to itself. If and only if this norm here is finite. You take the supremum here over all orthonormal sequences, Fj and Gj. So that's one way to define it. You can also work with the singular values, etc. So there are different ways to get the same norm, actually. So what we put here, we want to work with symbols instead of operators. So what you can do is that you can take this class here, all temporal distributions, such that the corresponding pseudo-differential operator belongs to IP here, okay? And you introduce this as your norm, okay? And it turns out, actually, that you have seen this before, that if p is equal to 1, you get the trace class operators, 2, you get Hilbert-Schmidt, and infinity, the continuous operators. And actually, by the Schwarz-Kernel theorem, it turns out that this map here is from this symbol to an operator is an isometric bijection. So this shows that you can really translate everything from operators to, let's say, distributions. So that's the main idea here, okay? So this is a consequence of the Schwarz-Kernel theorem. What are the rank 1 operators? Well, they became the A Wigner distributions. So you define it in this way, okay? For F1 and F2. And then it turns out that if you take an operator with such a symbol, you get just a rank 1 operator of this kind. And you can also see here that you can also express the action of this pseudo-differential operator acting on F and a scalar product with G by taking a scalar product between the symbol and this, okay? This is somehow a very equivalent description as we have seen before, actually, in other contexts. Yes? F1. Ah, okay, yes. F1 should be here. The second, yes, that's true, okay. It was correctly written before, but someone mixed my file before I came here. So this is for sure, yes, so that's happened. Okay, it's also convenient to actually have this kind of set of sequences. So this is the set of sequences where they where these values tend to 0 when j tends to infinity. Well, actually, this is explained here because what we can say about the spectral theorem is that if you just translate the spectral theorem for compact operators on L2, it becomes like the following. Any such symbol can be written as an expansion of such Wigner distributions, where these Fj and Gj should be orthonormal sequences on L2, and lambda here is in L sharp, okay? It turns out that these corresponding operators, they become the set of compact operators. But you can also, of course, talk about the translation of these Schatten symbols. And then you just take, instead of L sharp, which is we take as the L infinity norm, we can just take LP here, okay? That's it. Okay. Now we come to Orlicz spaces. I don't know, this is not mentioned here before. And actually, this is not something that I studied originally, but I got some sort of guest PhD students. And of course, the guest PhD students, if you were in the dark side before, perhaps you come even closer to a real heavy black hole in the end, okay? And I found that it was something interesting here. So they are extension of Lebesgue spaces. So what this Lebesgue exponent is essentially replaced by a so-called Young function. It's a convex function and it should be non-negative. It should be 0 at 0, and its limit at infinity must be infinity. Okay. And it turns out that if this should be fulfilled, then this phi must be actually increasing. So this follows from these conditions, okay? And then the Orlicz space here. This is the formal definition. You take a positive measure here, mu. So they should be all mu measurable, such that this integral, at least for some positive lambda, this should be bounded by 1, okay? And then you take the smallest lambda here, the smaller lambda you choose, the larger this becomes, because phi here was, well, it's increasing, okay? So that's the definition. Some example. First of all, our most common choice of a measure is, of course, the Lebesgue measure, and when we had the discrete situation, like this, okay? So this is actually those situations that we are encountering in this talk, okay? What happens if we choose this phi in different ways? Well, of course, a very good choice is when p is less than infinity, you can choose it like this. And if p is equal to infinity, you choose it like that. And then you actually get the classical Lebesgue spaces then, okay? Like that. And with the same norms. We can also take an example where this is a classical example when they found that this is very good to use Orlicz spaces. So if you have this entropy functional, then it turns out that you get really better result if you take Orlicz spaces instead of Lebesgue spaces. Actually, I have another collaboration with Anupam and two others where we actually discussed the Orlicz modulation spaces. And it seems actually that this is a field that when there are a lot of investigations about Orlicz spaces, but Orlicz type spaces where you replace the usual Lebesgue norm by, let's say, an Orlicz norm, for example, in modulation spaces, and as we shall do here with the Schatten classes, very little is done actually. And I think the experience so far, it seems that you can gain more by replacing the usual LP norms here than in the pure Orlicz space situation. For example, in that paper, we could really prove some interesting result about not this entropy functional, but another entropy functional. And it really gets better result by using a suitable type of Orlicz modulation space. This is this is not so much quantum harmonic analysis, so I cut this now, okay? So instead we shall try to continue with our quantum harmonic analysis. Before we continue, we can just see two things. First of all, we can see here that if phi2 is less than phi1, well, it's essentially, it's enough to check this close to 0 and infinity. Then you get, how to say, the Orlicz space then is decreasing with respect to the Young function. For the discrete situation, we can actually say a little bit more. Then it's enough to just check these relationships when t is close to 0. So in this situation, this space is completely determined how phi is behaving close to 0. You don't need to check how it looks for a little bit larger t, okay? That's an important thing. And this is also important when we are going to discuss later on this Orlicz Schatten classes. But before we do that, there are a few concepts. There is called conjugate Young function. And there is also something called the delta 2 condition, which is usually assumed, not always, but and why is this assumed? Well, because if this is satisfied, first of all, the Schwarz space is then dense in our Orlicz space. Secondly, the dual is given in this way, okay? And this is not only for, this is actually for, it could be L phi of mu here, okay? It's true for any measure here. So that's it, okay? That's why it's interesting here. A lot of, usually this is satisfied, but there are some examples where this is violated as well. So now we come to Orlicz Schatten classes, and they are, of course, defined very analogously as the usual Schatten classes. So this is exactly the same norm as we had before for the Schatten classes, but instead of having LP, we now have an L phi here, okay? There is no reason to make this more complicated than it is, okay? And the supremum is still taking over all such orthonormal sequences, Fj and Gj. And we also introduced these Orlicz Schatten symbol classes, which is the set of all symbols giving right to giving such a Schatten phi operators. And we regain in usual way the usual Schatten classes and etc. by choosing our Young function in this way. And it turns out that also in this situation, this map by the same argument is an isometric bijection. So again, we can translate things from pure operators to distributions, if you so prefer. Yes. And because, so this is a little bit what we said before. We can also see here that since we have just that if you decrease your Young function near t equal to 0, then you increase. This is phi 2 should be here, okay, not phi 1. Okay. And this is because we have a discrete L phi norm here, and for discrete L phi, this was the case. Okay. If this is not 0 for t greater than 0, then our Orlicz Schatten classes are a subset of the set of compact operators. And if this is satisfy this delta 2 condition, then this I1 is dense in I5. And the Schwarz class is contained here, and this is in both of them are dense in here, okay? So this is what we have. And we also have nice duality properties. So if phi is a delta 2 satisfy this delta 2 condition, then the dual of this is just with this conjugate Young function, and the same here. When we are using we have seen these forms before, so this is the scalar product among the Hilbert-Schmidt operators, if T and S should be Hilbert-Schmidt operator. And here, when we are now using symbols, we can actually replace this scalar product with the usual L2 scalar product. And somehow this is yes, so that's it, okay. I can just give one explanation why one should look at Orlicz Schatten classes. And I came actually to something that I never worked with by myself, but actually this Dixmuir trace is a so-called non-normal trace. And it has been used, for example, when you're looking at certain problems of pseudo-differential operators acting on manifolds, actually. And for example, Kohn used this in his analysis when I think it was one of the reasons why he once got the Fields medal, is that he made something with this Dixmuir. He proved that this is some sort of the same as a residue in certain type of residue in this field, okay? But what is interesting is that at least we didn't put this yet, but first investigations shows that this Dixmuir trace is not suitable on the classical Schatten classes because it's trivial on the set of trace class operators. So this is all such operators get Dixmuir trace 0. This is they're not so interesting. But as soon as you take p larger than 1, it's actually not continuous anymore. But if you take this as our Young function near t equal to 0, then you get something that is non-trivial as well as continuous. Okay, this could be a good motivation why one could, for example, look at Orlicz Schatten. Okay, and we can also see here that this class here is really between trace class operators and this Schatten P as soon as P is larger than 1. So it becomes between all these operator classes. Okay, for the while case, we can actually see a little bit more structures here. We have this symplectic Fourier transform that you have seen before, and we then put these names of these symbol classes. And it turns out actually that if phi is a Young function, etc., then the symplectic Fourier transform is an isometric bijection on these classes. It's not difficult to see this actually if you go to, for example, the spectral resolution of this, as we discussed before. Okay, now we come to the Young inequalities in quantum harmonic analysis, and this is what the Werner, you have seen these convolution relations before. Actually, if we choose to formulate these convolution relations by Werner from 84 in terms of the symbol level, well, as you remember, you before had convolutions between operator, convolutions between function operator should be an operator, etc. Here, just one convolution. And this is the ordinary convolution between functions and distributions, okay? You don't need to introduce any kind of new type of convolution in this approach, okay? And then you actually get these kind of estimates for these things, okay? And now we come to our extension. So what we are able to do is actually to make this in the context of Orlicz spaces, okay? This looks a little bit nasty, okay? This easy condition is, but there is also some structures here, okay? And we are not able to get that nice constant. So if you choose here phi 1, phi 2, and phi 0 in such way that we have this condition here, okay? We don't get that good constant here, okay? This is, at least on this level, we didn't put too much efforts to get the best constant here. This is what we could get here. As a corollary, usually we should always choose, so here we choose phi 1, so this class here agrees with the Schatten 1 operators. Then you get this kind of convolution relation here. So if you convolve L phi with a trace class symbol here, you get Schatten phi symbol, okay? So this looks very similar to what you have seen before, but now for the Schatten classes, okay? You can also get convolutions between symbols and symbols, and then you get, as usual, a function here, okay, in L phi. Okay. You can also actually get extend. This is a relation that is, I don't know when it appeared for the first time, but I actually had this in my thesis because I thought that Werner didn't. But I think for sure Werner could have, I don't know if he has it in his paper from 84 or perhaps some papers later, but at least this result in the situation of usual Schatten classes is from, let's say, at least you can see it from my own thesis from 96, actually. So this says that if you have a compactly supported distribution, then it is a Schatten phi symbol if and only if its symplectic Fourier transform is an L phi, okay? So this is what we can prove here. And we can just show how proofs work when we are working purely with symbols, okay? So we are using this convolution result here. So we have A here, but we assume that it's also compactly supported. So this means that if you take phi in the Schwarz class, so which is equal to 1 in the support of A, then this is of course equal to this, and then we can use the fact that these classes, they are invariant under symplectic Fourier transform. Okay? And then we can use these convolution properties to say that you have this estimate, and then suddenly you have this. You can see that the norm of this with respect to S phi is less than equal to a constant times the norm with respect to this symplectic Fourier transform of L phi. And in the same way, if you take we can use this type of the other convolution, okay, to get the opposite inequality, and then you get the equivalence, okay. So this is what we have, okay. So for compact K, we have that as long as A stays in this compact set, these norms are equivalent, okay. I think I have not so much time to go through the proof, but I can just mention here that this to get this result, we are using this kind of some sort of a technical lemma, of course. What happens if you take convolutions of such expansions of Wigner distributions, okay? Where this F2J, etc., they should be a set of orthonormal sequences, okay? And then it turns out that you can have some nice type of estimates, and this is some sort of a Schur type, and if you put this into your computations, you will actually get, together with the estimate of these Young functions we had, we get the result, okay? Okay, I don't know, I think I skipped this proof, and I want just to show sorry for this. I don't think any one of you could follow that, okay? I can also say that by using this symbol approach, I think this is actually another convolution result that I had once upon a time, a long time ago. And here I would say that I could find this. It was not so easy to find it, actually, when I worked with this once upon a time. But I think that why I could find it was that I was working on a symbol level. I'm rather sure that if I should have been working on an operator level, I should really never find this kind of convolution result. What is the difference here? Well, it is that you have now Schatten symbol that you dilate a little bit, okay? And if you make a convolution, you get another Schatten symbol. And this is what, as far as I know, not existing in the paper by Werner. So this is something other, okay? So this result is not was that way. And now, of course, we can extend this in a similar way by also to the Orlicz Schatten situation, okay? This is somehow a possibility. And just I want just to show a little bit how we can apply this, for example, to the Toeplitz operators. We have worked, so this is the same as, at least in this situation, localization operators. So these are our convolution, well, some of our convolution results now that we shall work with, okay? What we also mentioned for this kind of, when we had the Schatten convolutions, is that if we know that while operator of A and while operator of B are positive semi-definite, then this here should also be positive semi-definite. Okay. I think this should be a Virtual phi here. But in any way, this is the definition of Toeplitz operators that you have perhaps seen in other talks. And what is interesting here is that we can actually formulate the while symbol as a convolution between this Toeplitz symbol and a Wigner distribution, which is an element of, it's a rank 1 symbol, okay? So it belongs to all these Schatten symbol classes. And what we can then say from these convolution results is that if A is an L phi, then this Toeplitz operator here must be a Schatten phi operator. Secondly, we had problems with this dilation property, is that if we instead have a dilated version of our symbol as a Schatten phi symbol, then still our Toeplitz operator is also a Schatten phi operator. And what is also here is that if phi 1 is equal to phi 2, and this here is greater than or equal to 0, is positively semi-definite, then this Toeplitz operator becomes also positively semi-definite. I think this was everything, so I thank you very much for your attention.